they spent billions of dollars to try and prove that CO2 was the culprit by trying to correlate between the rise of CO2 in the atmosphere and the rise in temperature. So they assumed the answer in advance. Assuming the answer in advance is probably the worst sin you can commit as a scientist.
Our Bay Area Innovator today is Dr. Digby Macdonald. He has published over 1,000 papers in peer-reviewed journals and conferences, has 11 patents, and in 2011 he was nominated for the Nobel Prize in Chemistry. In 2023, he was nominated for the Fermi Award, which is the top nuclear award in the United States.
And the site vice president was standing at my door, and he grabbed my hand and he shook my hand. I thought he was going to break my arm. Shook my hand and he said, "You did it, you did it." He said, "The crud's come off the boilers, it's been collected in the filters, but you cannot say anything to anybody about this."
He is also a member of the CO2 Coalition, which is primarily our topic today.
That CO2 is not a pollutant, not at all. It's plant food, and there's a direct correlation between the crop yield and the amount of CO2. You know, we're able to feed about approaching 9 billion people. If we can't do that, 2/3 of the world will starve, will make global warming look like peanuts.
This is Bay Area Innovators, and I'm your host, Steve Ispas. Professor Macdonald, welcome to our program.
Thank you.
Well, glad to have you here. You've been with UC Berkeley for many years, and you've been recently nominated for the Fermi Award, which is the highest award in nuclear energy in the United States. Now, please tell us what specific contribution was the award you were awarded for?
Yes, when I joined Atomic Energy of Canada Limited, which was my first job, I was given the task of understanding the water chemistry of a CANDU reactor. And Douglas Point was the prototype for the CANDU reactors. And so I'd set up some what we call in-reactor loops at the Whiteshell Nuclear Research Establishment in Manitoba. And I noticed that if I changed oxygen and hydrogen, that the electrochemical potential would cycle over a wide range. This was all at 300 degrees centigrade. And so it turned out that when they started at Douglas Point, the radioactive elements of the crud, the corrosion products, would travel into the core, would settle on the core, would be irradiated with neutrons, and so cobalt-59 would become cobalt-60, which is a hard gamma emitter. And then it would be transported out to the boilers. But the area where the boilers were was not designed to have radioactive materials, so they had to get the material off the boilers and into the sumps where it's designed to be collected. And so I was invited to a meeting, and at the meeting a gentleman named Barry Monford, who ran the meeting, invited me along because everybody else was a nuclear engineer or a mechanical engineer. And they said, you know, we may need to know something about the chemistry. So I'm sitting there minding my own business, and the nuclear and mechanical engineers were talking about a thermal shock and a pressure shock, and I kept thinking, you know, these people don't understand chemistry. You know, that's not going to get the crud off. And so I'm sitting there, and Barry looked at me and he said, "Digby," he says, "what would you do?" And I thought, okay, I better give him an answer. I would do a redox shock. Redox, what's that? I said, that's the oxidizing power of the solution. So I would change the oxidizing power cyclically, and by cyclically pumping oxygen and then hydrogen, then oxygen, hydrogen, and so forth, until the crud came off. And he said, well, how would you do that? Well, I said, I'd take some cylinders of oxygen and hydrogen down to Douglas Point, and I would valve them into the feedwater system and, turn them on. How long? I don't know. I said, just turn them on and give them a shot. Okay? And that was on a Friday. And on the whole weekend, I thought to myself, I shouldn't have told them this, because nobody got permission to carry out an experiment on an operating reactor. It's a big crime if you do that. And so I got back on Monday morning, and the site vice president was standing at my door, and he grabbed my hand and he shook my hand. I thought he was going to break my arm. Shook my hand and he said, you did it, he said. The crud's come off the boilers, it's been collected in the filters, but you cannot say anything to anybody about this. He says, I want you to promise me that you won't talk to anyone, kids, wife, whatever, okay? And I said, okay, I can keep a secret. And so that was about 1972. And then about 1995, I was sitting at my office at Penn State. The phone rang, and the guy said, the other end said, he said, I don't know whether you remember me, and he gave me his name. I said, yes. I said, you were at Chalk River. That's correct. He says, I was at Chalk River. And he says, do you remember the Douglas Point incident? I said, I'm sorry, but I can't talk about it. And it took him maybe 5 or 10 minutes to convince me that he could, I could talk to him about it. He said, look, it's known, it's been published in a book. Everybody has been forgiven because it saved the CANDU net reactor program. And for that, he said, we want to award you the W.B. Lewis Lecture. Now, W.B. Lewis was a British physicist who went into Germany after the defeat of Germany as part of a team to determine how far the Germans had got towards a nuclear weapon. And the conclusion was that you had to either use enriched uranium or plutonium. And W.B. Lewis said, nonsense. He says, I can get a reactor to work with natural uranium, 0.7% of uranium-235 in the 238. And so when he
and that's true. That's true. You can do that. Right?
Yeah, he immigrated to Canada.
Yeah.
He became friendly with Prime Minister, and that's how Atomic Energy for Canada was set up. And they took Myrna and I on visits to all the nuclear sites around Canada. They treated us like royalty, and we had a big dinner in New Brunswick in my honour, where I gave a talk on it, and that's how Douglas Point and Atomic Energy of Canada came about.
Yes, you are a fellow of the Royal Society of Canada. Yes.
And of New Zealand.
And New Zealand as well. Now, let me change topics. I want to ask you about the CO2 Coalition. This is a group that you've been part of together with hundreds of other top scientists around the world. So
Right.
first, tell us a little bit about what is the CO2 Coalition? What does it do?
Yeah, that's another interesting story, because again, it involves Canadians. For some reason, the
Canada's in the news lately.
Canadians seem to come up with all these controversies. Okay, the story goes like this. Maurice Strong was the CEO of Ontario Hydro, which is the largest utility in North America. And it's the one now that runs many nuclear reactors in Canada. And Maurice was also a member of the Club of Rome. And I don't know, you're probably too young to remember the Club of Rome proclamation that they decided that the human race should return to the pre-industrialized state. Okay, and they needed to find a culprit to justify that. And they settled on CO2. They accused humankind of producing what we call anthropogenic CO2. And that was bad for the climate. Now, at that time, the IPCC was about to be set up, and Maurice Strong was sort of the guy behind the scenes who manipulated everything. And so the IPCC...
Let's tell our audience, IPCC is the Intergovernmental...
climate change.
Okay.
IPCC ended up by seeking to prove that CO2 was the culprit, not to find what the culprit was.
The culprit for temperature increase,
right,
or global warming. Okay.
Right. So they assumed the answer in advance, which violates the scientific method. So it's not based on science, it's based on politics. And that's why I had nothing to do with them. Instead, I joined the CO2 Coalition, which is a much more scientifically valid operation. Yeah, the goal of the CO2 Coalition is to introduce the scientific method, which is unknown to most lay people. Introduce the scientific method at high schools so that people come out with a basic understanding of what science is all about. Okay, and then they can spot these attempts to fool us by proposing non-scientific approaches, and assuming the answer in advance is probably the worst sin you can commit as a scientist. Anyhow, they spent billions of dollars to try and prove that CO2 was the culprit by trying to correlate between the rise of CO2 in the atmosphere and the rise in temperature. But they forget causality does not arise from correlation. In other words, you can have a correlation and the process can be non-causal, and hence without a scientific basis. And so just having a correlation was not sufficient to prove that it was scientifically valid.
I think you give a good example in your paper about the causality principle. Is you have a gun, you pull the trigger, and then the gun shoots.
Right.
It doesn't shoot before you pull the trigger.
Hopefully not.
Right. So there's a cause and effect.
Right.
So tell us about that, how that relates to...
Right. The causality principle itself says that every effect must have a cause, and the cause must precede the effect. That's the main statement. And then there's a second statement that regards multi-step processes, that if any one of these steps is non-causal, then the whole thing is non-causal. Now let's take the gun. Clearly, the cause is you pull the trigger, and the effect is the bullet comes out the end of the gun. That's the causal thing. That's one that is valid on a scientific basis and occurs. If you had a gun that fired before you pulled the trigger, that's clearly non-causal. That's against the intended purpose of the gun and against the science and mechanics of the gun firing mechanism. Now, I dare say there have been accidental firings of guns, okay? But in no case can it be attributed to a violation of the causality principle. So that's what causality is. It has a very highly mathematical basis in Cauchy's theorem, from which stems the Kramers-Kronig transforms that I and Werner have used extensively in our work on electrochemical impedance spectroscopy for exploring electrochemical reaction mechanisms. So it's a fairly simple concept.
So tell us how that relates to the CO2 and temperature.
Right. For the IPCC to be correct and Morris Strong to be correct, you must have the situation where the CO2 rises first, that's the cause, and the effect is the rise in temperature.
Which is what a lot of people think it's happening, and
then
they assume it's happening.
They blame the rise in temperature on the rise in CO2. But they didn't check the causality relationship to see if that's valid. And that's what I did.
So what did you find out?
I found out that, in fact, temperature rises, and then the CO2 comes out. Okay? And
So
if the temperature falls, the CO2 lowers in the atmosphere. It goes somewhere. Well, where it goes is that the oceans are an enormous repository of CO2. Naturally, that CO2 eventually combines with carbon ions to form limestone in the ocean.
So let me sure I get that right. So from your research and your experimentation, and not just yours, but the other scientists in the CO2 Coalition, you are saying that the temperature rises first, and that's the cause, and then the effect is that the CO2 increases.
That's correct.
Following the temperature.
That's correct.
Okay.
And that's the very reason why you put your beer in a refrigerator or in any fizzy drink. So if you want the fizzy drink to be tangy, and at some later time after you open it, you put it in the refrigerator so the CO2 remains in the refrigerator, in the drink. As I pointed out earlier, you can go to Britain where they drink flat beer, where there's, the CO2 is out, and in New Zealand the same thing, Australia the same. So what you taste is not the tangy taste of CO2, like a fizzy drink, but the beer taste itself. And so some nations prefer that.
Please tell us how you and others have determined that this is the case, that
Right.
the temperature drives CO2, not the other way around.
Right. We needed records. And prior to the development of instrumentation in the late 1800s, the only records are what we call proxies. That is, some property of what we're looking at depends upon the concentration of CO2 when it was formed, and the temperature is reflected in, turns out, in isotopic distributions. So let's deal with the temperature. The bubbles of gas that are trapped in the ice are analyzed by spectroscopy, and they give us the concentration of CO2, but it also gives us the oxygen 18 to oxygen 16 and the hydrogen 2 to hydrogen 1, so deuterium to hydrogen ratios. The conversion of deuterium to hydrogen and oxygen 18 to oxygen 16 occurs by the emission of particles, and that's known in great detail. I mean, we've got very good numbers for that. So by calculating how the ratio that exists when we observe it, and which was frozen when the CO2 was trapped, we're able to calculate what the temperature was back then.
I see. So basically from the ice that's formed, you can determine at that point in time, hundreds of thousands of years ago, what the CO2 level was.
Hundreds of thousands.
Or a long time ago. You can determine just from the ice that can be found where in the Arctic or...
That's correct.
Mm-hmm.
Now there are other proxies. You're probably aware of the famous hockey stick
Mm-hmm.
controversy. Michael Mann, who was a colleague of mine at Penn State, he used tree rings because he claimed that the number of tree rings was a function of the temperature. So he used that as a proxy. It turns out, again, as discovered by Canadians, it turns out that that's not very good. Not very good at all. And if you replot the hockey stick, it doesn't look like a hockey stick. There's no sudden rise in temperature. And so that was, I mean, big lawsuits were fought over that and so forth. So that's how important it is.
How do we compare now the temperature, the global temperature, compared to the past? Where are we?
As I can show you in a graph, both the CO2 and the temperature have swung over wide ranges. Right now we're not particularly warm, but if you go back to 100 and something years, people were skating on the River Thames in London, and that was called the mini ice age because the temperature dropped to quite a low value. So we're actually recovering from a mini ice age, and so the temperature's got nowhere else to go but up. Okay, and that's what it's doing at the moment. It's got nothing to do with CO2. It's the fact that
But so right now we are not at the highest global temperature. We are in the middle somewhere.
During the Roman period, we had temperatures much higher than they are now. I mean, when I say much higher, 2 to 4 degrees higher, but people were growing citrus fruit in northern England. Greenland is named Greenland, even though many times of the year it's covered completely with ice. They don't call it white land, okay?
Yes.
They call it Greenland because it was when the first explorers went there, the Vikings, it was during a warm period. You know, plants grew and it looked green. So you can go back in history and trace these changes. So the temperature has swung all over the place.
How about the level of CO2? Is it now at a historic high, or what? Where are we right now?
Historically, and I'm talking about millions of years, we're at a low period.
We're in a low period. Okay.
Right, and this is important.
Yes.
It's important because if you drop below 150 parts per million, plants don't grow. Photosynthesis doesn't occur. And so we would have no carbohydrates in which to feed the population.
If it was 150 parts, now it's around 400.
Now we're about 420.
Mm-hmm.
Okay? The optimal level for plants to grow is 1200.
1200.
Right. And there's been experiments done where they've, you know, when a person operates a hothouse, what do? Well, they want to get the temperature high.
Yes.
But for photosynthesis, they want to get the CO2 high. So they pump CO2 into the hothouse to grow their tomatoes.
This is amazing. So I have to ask you again. So the CO2 levels right now, it's about 420.
Right.
And you're saying the ideal for plants to grow is about 1200.
That's correct.
But everyone is so worried that we're too high already.
Right. Well, sailors in submarines operate at 1200 parts per million. Astronauts operate at 1200 parts per million. The more CO2, the better. And there's a direct correlation. Again, correlation is not causality, but it's indicative of the trend between the crop yield of things like corn and wheat and soybeans and so forth, and the amount of CO2. And a lot of we're able to feed about approaching 9 billion people. simply because the crop yields have risen to the point that we can make enough hydrocarbon food to feed people. If we can't do that, we've got a catastrophe that will make global warming look like peanuts.
Wow.
Okay, because 2/3 of the world will starve, and they'll be condemned to forever poverty. That's what the issue is. So
That's amazing.
So the CO2 Coalition emphasizes that CO2 is not a pollutant, not at all. It's plant food, and it's a very important part of the photosynthesis cycle. So people will eat the food, and that CO2 will eventually be released back to the atmosphere. So the people are just, if you like, intercepting the energy that is stored in the carbohydrate by the simultaneous irradiation by the sun and water and CO2. They eat the food, which builds their bodies, okay, and at the same time they're releasing that CO2, and so the CO2 will go back into the cycle. And that cycle is very important for poverty and starvation of 2/3 of the world's population.
So you are basically saying that not only the CO2 level is not too high right now in the world, but it's not high enough. It actually
That's
should
correct.
be more. Should
That's
be more
correct.
for plants to develop and to.
It's not high enough. My personal choice would be between about 800 and 1,000.
Wow, that's amazing.
So we've got a long way to go.
Right.
But
Now, if CO2 is not what drives the increase in temperature on Earth, what does?
if it's not,
Yeah, if it's not the CO2 that drives the temperature to
what
increase.
does?
Yeah, what does?
Oh, well, that's the cycles of the Earth. For example, the basic cycle is the Milankovitch cycle. That's the cycle around the sun. Well, that cycle changes every 100,000 years. It changes so that you have an ice age when it's the most elliptical. So you'd think of the sun being here and the Earth comes elliptical like this. When it's out here, it's receiving a lot less solar radiation and a lot less heat. Okay, and then it comes back and it receives heat, and it goes. But the net effect is that it produces ice ages every 100,000 years. So that's the basic cycle. That was Milankovitch. If you read about him, he was a bit of an oddball. He was a astronomer, physicist in Russia, and he proposed this theory. Nobody understood what he was talking about when he proposed it, and he worked out all the mathematics, and that's known as the Milankovitch cycle. Now, on top of that are numerous other cycles. For example, the Earth is spinning like a top, and the axis between the North Pole and the South Pole with respect to the Milankovitch plane, that varies over about 22,000 years. And that's very important for climate change. So there are many, many different cycles that occur that have cycles between 100,000 years and as short as 10,000 years.
So you're talking about the angle that the Earth is spinning, right?
Right.
It's about 20-some degrees, right? And
Right.
sometimes that changes.
Well,
and
yeah. And right now, the Milankovitch ellipse is almost circular.
Mhm.
Okay, so we are in a situation where the Earth is being more or less evenly irradiated. It doesn't matter whether it was in summer or winter. Okay, so other cycles are clearly important in still preserving the seasons. So it's...
Are there other factors like the sun?
And then sunspot activity, the output of the sun. It's known that the sun, which involves the fusion what we're trying to do to produce electricity, the fusion of the light elements are going to produce the heavy elements. That's where the heavy elements are born, are in the centre of these stars, like the sun. Goes through cycles that are right now little understood, but certainly the impact and the irradiation that is coming out is very detectable. So is the sunspot activity, which is, I like to think of it as being a symbol of the energy being produced by the sun. If it gets too much energy, it sort of comes out through these areas which change colour on observation. So the sun is very important. Some people believe that cosmic radiation from far outer space is important, because the cosmic radiation comes in it causes ionization of ions in the atmosphere, and that's why you get the aurora borealis and so forth, the northern and southern lights. It's simply a manifestation of, but we don't know whether the solar radiation is coming, cosmic rays are coming primarily from the sun or from outer space.
So you are saying that the change in temperature on Earth is mostly to do with the different cycles of the Earth and the sun.
Correct.
And mostly nothing, if almost zero, has to do with the human activity.
There's nothing that you and I can do about that.
Yeah.
That's okay, because if we rely upon the historical record, we go through these maxima and minima. It turns out that civilization advances the most during the maxima. During the Roman period, there was a large advance in civilization, and that was during the Roman maxima. But there would be many maximum and minimum. Mm-hmm. And so we are right now, as far as temperature is concerned, we're about a quarter of the way up between the low minimum and the high maximum.
So we're still on the low side.
Right. So we've got a long way to go. And you know, the changes are very small. We're talking about, in some cases, fractions of a degree.
Yes.
Centigrade.
Now I have to ask you this. Worldwide, and probably with the U.S. leading this, it's between $1 to $2 trillion being spent every year.
Correct.
To address CO2.
Right.
And to eliminate CO2.
Right.
I think the European Union has spent $1 trillion as well on their
Right.
programs.
Right.
What can you say about that?
It's welfare for scientists. Is one way of looking at it. You know, it's supported by a huge propaganda effort, which is not based on scientific fact, and it's all political. This has been demonstrated many, many times when the IPCC publishes their reports. People have gone through and they've found that what's claimed in the report simply isn't supported by the data that is in the report.
Yes.
So there's that problem. Again, they set out to prove that CO2 was the culprit, not to find what the culprit was.
Right.
So if they set out to find what the culprit was, which is the scientific way of doing it, they'd find certainly that water vapor was the only gas in the Earth's atmosphere that keeps the Earth warm, and that's a paper by Lightfoot. You know, the impact of CO2, methane, and nitrogen oxide are immeasurable. And if a thing is immeasurable in science, it doesn't exist. So why do they spend so much money? Because it's a propaganda effort, and certain people have taken it upon themselves to show that it's CO2 regardless of what the truth is.
Would you say that most scientists, at least the scientists in the CO2 Coalition, which is a few hundred of them, we didn't count all of them, but there's a few hundred, would you say they share the same understanding as you on this?
Yes.
They do?
Yes. We have many different professions, geologists, chemists, physicists and whatnot. And John Clauser was the Nobel laureate in physics about 3 or 4 years ago. He's a very knowledgeable guy, but there's people like Will Happer, who is a very famous atmospheric physics guy. And then we've got other guys who are experts in the ocean movements and all of that sort of thing. So we haven't yet covered all of the topics because, you know, people join. We get probably 4 or 5 new members a year. We've got some outstanding people in the CO2 Coalition who understand the science, and there's been many debates between people from the CO2 Coalition and the climate activists, and every time the scientists have won the debates. There's no question about that.
Using scientific means to explain.
And they've just launched a very active education program that's aimed at K-12 level to bring the truth out about climate change. And again, the term climate change is an oxymoron. You know, you have to understand that weather, we can have many different weathers occurring in nearby areas. So the weather in San Francisco is probably distinguishably different than the weather in Santa Clara,
Yes.
right?
Yes.
And so there's no single weather on the earth. There are many weathers. And the definition of climate is the weather integrated over 3 months. Well, that also leads to many different climates, not one climate, okay? And so that's what we're dealing with. If you're worried about this issue, say, in Hawaii, it's different than it is in London. And so transferring data from one to the other is a very tricky process. You have to be very careful.
I want to ask you about the models, the IPCC models. So again, Intergovernmental Panel of Climate Change.
Right.
They have these models they use to show this relationship between temperature and CO2.
Right.
What can you say about that? Are the models wrong, or how do they come up with these results?
The models are incorrect because in order to solve the equations, you have to make gross approximations. And it turns out that all of these models overpredict the climate change, so-called the temperature, by a wide margin. It's not even close. And what's the problem? Well, you've got models that describe chaos, for example. To put it in mathematical terms, you've got second or higher order differential equations that are coupled. Many of these equations are coupled one with the other, and to find the solution of that is very, very difficult. And in order to get a solution, they make approximations that destroy the purpose of the model. And that's the problem. Now, I'm not blaming them. You know, they're given the job to do it, and they've probably done as good a mathematical work as you can possibly do. But this is such a complex system that you can probably never get a solution that is 100% accurate.
So again, I think what you're saying is the issue is that the scientists are given the task to prove that climate change happens because of CO2, and they're focusing their effort on that
Right.
instead of trying to find out what really contributes to
That's
the
correct.
rise in temperature.
That's correct. And that goes all the way back to Maurice Strong. These Canadians have had a...
Yes, yes.
I'm a Canadian citizen.
I've seen on the CO2 website an article about how climate change is not what caused the recent fires in Los Angeles. Any thoughts on that?
Maybe the weather did. Okay, but that's not climate change.
Mm-hmm.
Obviously, they've had dry conditions that produced a lot of tinder, and it all went up in flames, and unfortunately 25,000 houses went up with it. Yeah, so to blame the LA fires on climate change is to miss the real issue. The real issue there is that they had no water to fight the fires, and they allowed all this tinder to gather. Mm-hmm. Our son is a firefighter. He was fighting the LA fires, and I spoke to him on the phone. He says, "Dad," he said, "you know, this is terrible. Nobody cleared all the dry grass and the tinder from between blocks of houses." And he said that was one of the main modes of transmission of the fires. So, and no water. They didn't have any water to fight the fires. So I think President Trump pointed that out to them, and he's putting pressure on Governor Newsom to do something about it.
Yeah. Professor Macdonald, thank you so much for your time. Any final thoughts for our audience?
Yes, the trillions of dollars that you talked about would be far better spent on addressing other problems that we have in societies, both in Europe and the United States and Australasia, and Japan, China, and so forth. You know, we've got a massive problem in the United States of homeless people. And we've got massive problems of healthcare that people can't afford. Okay, and here we are spending trillions of dollars on something that is not real, while people die on the street, or they die in the hospital bed because they didn't have the right medication at the right time. So there are many, many problems in society that could be addressed effectively with that $1 trillion. And I think the politicians need to rethink very carefully what they're doing and what the implications are for humankind. Because the implications is that we would have mass starvation, and we would condemn about 2/3 of the world's population to never-ending poverty.
If the CO2 was really low, you're saying, right?
Well, yeah, well, no, just even if they don't affect the CO2, the fact that they're spending the money is being diverted from other issues. So the politicians, it all, in my opinion, rests on the shoulders of the politicians. They're the ones who make these decisions, and they should think very carefully. I know it's, you know, a popular subject to bring up during an election, because still there's a lot of people who believe the IPCC. They should tell the truth of what the actual implications are for humankind. And then I think the voters are sensible enough to make a choice themselves.
Professor Macdonald, thank you so much for your time. Really appreciate you being on our program.
Well, thank you.